Hi kids, let's recap what we have learned in chapter 2 and 3 in this particular video. The objectives of this particular video are as follows. Revisiting acids and bases, revisiting the concept of metals and nonmetals, revisiting the concept of chemical properties of metals, and revisiting the metallurgy. Now let us revisit the concepts of acids and bases. Acids are sour to taste. All acids contain hydrogen. In aqueous solution, they release H plus ions into the solution. When acids react with metals, hydrogen gas is released, as you can see out here. It turns blue litmus to red, as you can see here. Examples for acids are acetic acid, citric acid, sulfuric acid, etc. A base is a substance that is soapy to touch and bitter to taste. It releases hydroxyl ion in aqueous solutions. They turn red litmus blue, as you can see out here. Bases soluble in water are called alkalis. Examples of bases are sodium hydroxide, ammonium hydroxide, etc. Here you can see water being tested on blue litmus and red litmus. If you can observe carefully, you can see that there is no change at all. This suggests that water is neutral, neither acidic nor basic. Indicators are chemical substances that change color when in contact with acids or bases. Examples are blue litmus, red litmus, methyl orange, and phenolphthalein. We already looked at how litmus paper behaves in the presence of acids and bases, right? Now, here is how it behaves in the presence of different indicators like phenolphthalein, methyl orange, methyl red, and or bromophenol blue. In some, the neutral pH is also indicated by a different color. Here you can see how a change in pH brings about a change in the universal indicator. Acids and bases or alkalis interact with each other to form salt and water. As you already know, when a base is placed in water, it splits into its respective ions and basically it releases hydroxyl ion, and an acid in an aqueous solution releases hydrogen ion and the respective anion. So in here basically the positive and negative ions interact with each other to give you a salt, and OH and H plus interacts with each other to form water. This reaction is termed as neutralization reaction. The balance of hydrogen ions or hydronium ions and the hydroxyl ions determine whether the solution is acidic or basic. When hydrogen ions outnumber the number of hydroxyl ions, the pH is known to be low, and this low pH is generally considered as being acidic. Similarly, if we have more hydroxyl ions than hydrogen ions, such a solution is known to be at a higher pH, and that solution with a higher pH is considered as basic. Basically, pH is defined as the negative logarithm of H plus ion concentration in water. It stands for the power of hydrogen. pH helps us to quantify how strongly acidic or alkaline a solution is. A solution having a pH 7 is considered to be neutral. Here you can see that water is neutral. And you can also look at different substances that we use in our daily life and their respective pH. Strong acids like hydrochloric acid and sulfuric acids have a pH closer to 1. Strong bases like sodium hydroxide have their pH closer to 13 or 14. So basically, as you go down from 7, the nature increases, and as you go higher than 7, the basic nature increases. Salts are ionic compounds that have a cation other than H plus and an anion other than OH minus. You can look at different examples out here. They are crystalline and some are water soluble. They are good conductors of electricity. Salts like sodium chloride can be used as a preservative and to produce other chemical substances. Water of crystallization is the fixed number of water molecules present in one formula unit of a salt. Out here you can see two different kinds of copper sulfate. One which has 5 water molecules in it, or hydrated copper sulfate, and an anhydrous copper sulfate. Look at the difference. Here you can have a look at metals and non-metals present in a periodic table. As you can see, when you go left side of the periodic table, you can see the metallic nature increasing, and basically on the left hand side you can find all the metals in a periodic table. As you move towards your right, you can find more non-metals. So metals are on the left hand side of the periodic table and non-metals are on the right hand side of the periodic table except for hydrogen. And out here at the junction you can see metalloids, which have properties similar to both metals and non-metals. Now let's have a look at the difference between metals and non-metals. Metals are lustrous whereas non-metals are dull. Metals are sonorous whereas non-metals are non-sonorous. Metals are malleable and ductile whereas non-metals are generally brittle. Generally, metals are solids at room temperature since metals have a very high melting point except for mercury and gallium. Non-metals can occur in all 3 states. Bromine is the only liquid out here. Metals are good conductors of heat and electricity, whereas non-metals are bad conductors of heat and electricity. Metals have a high density, non-metals have a low density. Metals are very electropositive, hence form cations. Non-metals are less electropositive, hence form anions. Examples of metals are iron, aluminium, copper, sodium, etc. Examples of non-metals are oxygen, sulfur, carbon, phosphorus, etc. Metals and non-metals generally interact with each other to form ionic compounds like sodium chloride, sodium fluoride, magnesium oxide, etc. Now let's have a look at the reactivity series. We saw that electropositivity goes down as you go down the reactivity series, and then that the higher ranking metals are more electropositive and hence they donate electrons very easily and hence are very reactive when compared to the lower ranking metals. And we saw how it reacts with oxygen. Most metals react with oxygen to form metal oxides, some of which are basic in nature and some are amphoteric. And we also saw how it reacts with dilute acids. Any metals that are placed above hydrogen have the ability to displace the hydrogen in the acids and release it as hydrogen gas. Then when it comes to water, we saw that the reactivity obviously goes up as you go higher in the reactivity series, and again they form metal oxides, some of which are basic and some of them are amphoteric in nature. And the basic oxides are formed by reacting with water as such, but when it comes to certain metals like aluminium, zinc and iron, they interact with only steam, as the reactivity is lower than that of the higher ranking metals. And when it comes to salt solution, you do know that metals which are higher up can displace the metals which are lower in place in the reactivity series from their salt solution. We already saw the different aspects of reactivity series. It basically helps us to predict the way different metals and non-metals interact with oxygen, water, salts and acids. For example, potassium is more reactive than aluminium, which is more reactive than gold. Very reactive metals like potassium, sodium and lithium displace hydrogen from water. Example here. Potassium reacts with water to give you potassium hydroxide, releases hydrogen and a lot of heat. Slightly reactive metals like aluminium, iron and zinc form metal oxides when exposed to steam. Example is here. Aluminium reacts with water to give you aluminium oxide, releasing hydrogen gas. Some metals displace hydrogen from acids, and these metals are placed above hydrogen in the reactivity series. For example, magnesium reacts with hydrochloric acid to give you magnesium chloride and releases hydrogen gas. Some metals like gold, silver, etc. are not very reactive, hence won't react with water. Metals displace lesser reactive metals from its salts. Example, ferrous displaces copper from copper sulfate solution, giving out ferrous sulfate and copper. Metals form metal oxides that can be basic or amphoteric in nature. Non-metal oxides are either acidic or neutral in nature, like you can see here. Metal carbonates reacts with acids to form salt, water and carbon dioxide. Example, sodium carbonate or washing soda reacts with hydrochloric acid to give you sodium chloride, carbon dioxide and water. Metal bicarbonates reacts with acids to form salt, water and carbon dioxide. Example, sodium bicarbonate or baking soda reacts with acetic acid to give sodium acetate, carbon dioxide and water. So here is what we have learned till now. We learned that different metals are of different reactivity, and this we can understand using a reactivity series. And we understood that because of the varying reactivity, we might have to apply different methods to extract these three different categories of metals. So in here, first, let us start with the low reactivity series. So metals of low reactivity are generally sulfide ores, and by roasting we can obtain the metal, which can be further purified by refining. Metals of medium reactivity can be carbonate ore or sulfide ore. If it is sulfide ore, we use roasting or heating in the presence of air to obtain oxide. If it is a carbonate ore, we use calcination, which is nothing but heating in limited supply of air to obtain again oxides of metals, which can be reduced using elements like carbon. And once it is reduced, it can be purified further. Then let us move on to the metals with high reactivity. In this case, we use electrolytic reduction, as they are even more reactive than carbon, and we obtain the pure metal. You also learnt about corrosion and how we can use galvanization and alloying to prevent it. Thank you, kids. Hope you could revisit the concepts from chapter 2 and 3 along with me. If you have any doubts, please feel free to contact us.